It's one of the world's most powerful telescopes, ESO's Very Large Telescope, and this year is its 25th birthday. Time for a celebration and for a look back at its most exciting astronomical discoveries. Welcome to Chasing Starlight, the new hosted show by the European Southern Observatory ESO. I'm Suzanna Randall, I'm an astronomer here at ESO, and I have always been fascinated by the night sky and our universe. As a kid, in fact, I dreamt of going down to these huge telescopes in Chile to look at the night sky with them. So, several years later, I was thrilled to be asked to act as an astronomer on duty at the Very Large Telescope at the VLT in Chile. So my job there was to take the observations of the night sky and to find out new things about our universe. The VLT is really an amazing place, not just the night sky, which lets you see thousands and thousands of stars, but also the telescopes themselves. The VLT consists of 4 main telescopes, which each have main mirror diameters of 8 meters, and they can be used separately or put together to make one giant virtual telescope. And it is this giant's birthday. So the VLT is celebrating 25 years. And we decided to do something special for the birthday. So today I proudly present my VLT Top 5 Discoveries. When I first became interested in astronomy in the 1980s, one of the things I found it very hard to get my mind around was that the universe was expanding. And at that stage in time, it was thought that yes, the universe was expanding, but actually the expansion was slowing down. So I thought, okay, that's quite a peaceful prospect for the end of time. Everything will just kind of slow down and yeah, we'll be very, very zen. But then a group of scientists sets out to actually prove this theory. And to do this, they used a bunch of telescopes, including the VLT, over many, many years. And what they did was they observed a certain type of supernova. So a supernova is basically a huge explosion that happens at the end of the life of a massive star. So the type of supernova that the scientists use is called type 1a supernova for the more nerdy ones among you. And it has the property that, first of all, it's very bright. So that means you can see it out to large distances. And secondly, it always explodes at the same brightness. So we can use it as what we astronomers call standard candle. That means that basically you can directly infer from the observed brightness, so how bright it appears to us, how far away it is. And what the scientists found puzzled them, because they found that some of the very, very distant supernovae were in fact fainter than they should be. So that meant they were further away than they should be. And that meant that something was wrong with our models of the expansion of the universe. The expansion of the universe accelerating is actually a pretty disturbing prospect, because it means that at the end of time, which won't be tomorrow or the day after, but in a few billion years, it means that everything's going to be ripped apart. Not just stars, galaxies, but even molecules and atoms, including humans if we're still around. But as a consolation, at least some of these humans were awarded the 2011 Nobel Prize for Physics for this finding. For me, one of the most exciting things to happen in astronomy in the last decade was the discovery of gravitational waves. So gravitational wave, that sounds very abstract, and it is actually. Gravitational waves are ripples in the fabric of space-time. You can imagine this a little bit like a still flat lake where you drop a stone and that creates ripples. Just in the case of the gravitational waves, it's not a stone that is dropping into a lake, but it is in fact 2 very compact objects that are spiraling in towards each other and finally merging. And this creates this ripple in space-time. You can detect this ripple with a special underground detector called an interferometer, which can actually measure the short expansion and contraction, which is tiny, 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 in space-time as this wave passes. But when two compact objects merge, they should not just create this gravitational wave, but they should also create a very energetic light flash, a gamma ray burst. And in fact, we know gamma ray bursts, we've observed many of them, but it's extremely difficult to tie a gamma ray burst to a gravitational wave. So it was really quite a sensation when in 2017, just seconds after a gravitational wave event had been recorded by the underground detector, a gamma ray observatory in space found a gamma ray burst, a very bright flash of light. So for the first time, we were able to tie a gamma ray burst potentially to a gravitational wave event. And this was so exciting that all the big telescopes, as soon as it got dark, started pointing at that area of sky. And indeed, they found a new bright spot. Over the next weeks and months, ESO and the VLT launched a huge campaign in order to observe this object, or this explosion, more closely. And what they found was spectacular. This explosion had been a kilonova, and it had been caused by the merger of two neutron stars. So neutron stars are the very exotic, very dense end product of stars. They're kind of nearly black holes, but not quite. And I think this result is really amazing, and it is a very nice example of what is possible when international teams work together across different disciplines. Remember Oumuamua? That was the weird interstellar object that some people thought might even be an alien spaceship. Oumuamua was discovered in 2017, and it was the first interstellar object that we had found to be wandering into our solar system. The thing about Oumuamua was that it defied all expectations. It was really weird. So first we thought it was a comet, then it was reclassified as an asteroid, then it was a comet again. It really wasn't clear what it was. So the problem with these interstellar objects is that they're very, very hard to see. They're very small, so only a couple of 100 meters across in the vast expanses of our solar system. It's a bit like trying to find a mosquito in a dark room. As soon as you see it, it's gone again. And that was also the case with Oumuamua. So it took the power of the VLT to characterize this object. And what the VLT found was that Oumuamua is dark, reddish, highly elongated, and most definitely not an alien spaceship. But Oumuamua is not the only interstellar visitor to come and see us in our solar system. Just a couple of years later, we discovered 2I Borisov, the second interstellar object, named after its discoverer. This object was not quite as weird as Oumuamua. It was quite clearly a comet. But what made it special was that it was the most pristine comet ever observed. So that means that it really bears the signature of the cloud of gas and dust in which it was formed. Comets are a little bit like fossils in that way. So you look at the comet like you look at a fossil, and you can determine how and under what conditions they were created. What the VLT found was that the chemical composition of 2I Borisov showed the presence of heavy metals. And that is quite similar to some of the other comets found in our solar system. So you might say this is a bit weird because this comet has come from another stellar system, and yet it is very similar to the comets from our solar system. How can that be? Well, the only way that makes sense is if these other close-by stellar systems are very similar to our own solar system. Shouldn't the planets maybe also be similar? May there be a second Earth in another nearby stellar system? You never know. Maybe we'll find a real alien spaceship floating around in our solar system sometime in the near future. Until the 1990s, and when I was a kid, the only planets that we knew were those in our solar system. So our Earth and the other nearby planets. And according to what we knew then, and also what we know now, apart from potentially on Earth, there is no intelligent life anywhere, which is kind of a depressing prospect. Are we really alone in the universe? But in the 1990s, we started discovering exoplanets. So planets that go around stars other than the Sun. These are incredibly far away and actually very, very hard to find. What we normally do is we don't look at the planet itself, but we look at the light of the star that it orbits. So there are two main techniques to do this. The first one is that you measure the wobble of the star as the planet goes around it and gravitationally pulls on the star. And the second is that you look at the light of the star when the planet goes in front of it. So you get a little dip in light, the star becomes a little bit fainter, and you can say, ah, okay, I know there's a planet there. With these techniques, we can say that yes, there are planets, and we can say something about their mass and their radius, but we still can't look at the planets directly, and we can't say anything about what it might look like on these planets. In order to do that, we want to look at the planets themselves. The problem is the exoplanet is very faint and the star is very bright. It's a bit like trying to take a photo of a firefly that's right next to the lit headlamp of a car in hundreds of kilometers distance. So the firefly is just far too faint. The only way to get an image of the firefly is to separate it spatially from the headlamp, so to make a very, very sharp image. And in astronomy, in order to do that, we need something called adaptive optics, which in terms of engineering is a bit complicated, but in terms of the concept is very simple. So what we do is we correct for the effects of the atmosphere. The atmosphere makes stars twinkle, which is very nice if you're trying to have a romantic night, but very annoying if you're trying to take a photo. So with adaptive optics, we can correct for this twinkling and take super sharp images, and it was like this that the VLT managed to take the very first image of an exoplanet. This image caused really quite a stir, and not just in the astronomical community, but worldwide. This was the first time that we were actually looking at another world outside of our solar system, unimaginably far away. And to go with a beautiful image, the planet also got a beautiful name. You can see here. To make things even better, the VLT has since then not just taken more images of planets, but it has also taken spectra. In a spectrum, what happens is that the light of the planet is fanned out, and you can see the chemical composition of its atmosphere, which is of course super interesting, especially if you're looking for signs of life. But in the near future, ESO will have a new telescope, the ELT, the Extremely Large Telescope, which is currently being built right next to the VLT in Chile. And with the ELT, it may be possible to look at the atmospheres, not just of gas giants, but also of Earth-like planets. And who knows, maybe even discover the signatures of life. Finally, we're at the top of the list. So here is my #1 discovery with the VLT. Being at the VLT as an astronomer was always super exciting because you felt you were at the forefront of science and everything was happening right there. And on this particular night that I remember very well, a guy came to me with his laptop and he said, "Oh, you want to see something really cool?" And I was like, "Sure, why not?" And what he showed me was a bunch of stars moving around an invisible object. So these stars were kind of dancing and they were moving, but it was not clear why they were moving. And the guy told me that in fact they had been doing this monitoring, so observing how the stars moved over many years, and their measurements were getting more and more precise as the telescopes got better. The game changer here was once again, as with the exoplanets, adaptive optics, which allowed them to make sharper and sharper images in order to track the motion of the stars very, very accurately. But things got even better, because after all, we were at the VLT. So we had not just one telescope, but 4 telescopes. So an instrument was built where all 4 telescopes could be used together to get even more precise measurements of these stars that were dancing around. This instrument was quite fittingly called gravity. And there was, in fact, quite a rush to get it done on time because, as it turned out, scientists were converging on the idea that probably what was in the center of the galaxy was a supermassive black hole. And in 2018, one of the stars was about to pass very closely to the black hole, enabling us to test general relativity to an unprecedented level. So the instrument was ready just about in time, made the observations, and what we found completely changed our understanding of black hole evolution, formation, and once again proved Einstein right. For me, also something exciting happened. I was watching TV in 2020 and all of a sudden I saw Laptop Guy on the TV. As it turned out, it was Reinhard Genzel who had just won, together with other scientists, the Nobel Prize for Physics for exactly this discovery. Those were my personal top 5 VLT discoveries. But of course, they're just the tip of the iceberg. The VLT has discovered so much more. Over the last 25 years, the VLT has fundamentally changed our understanding of the universe we live in, from our own solar system, over nearby stars, the center of our galaxy, out to the edge of the observable universe. So, happy birthday, VLT. Please keep going, because there's still so much out there to discover. I really hope that you enjoyed this episode of Chasing Starlight. If you did, please press the subscribe button and also activate the notification bell. That way you'll be notified of any new episodes. If you have any comments, please leave them below. For every episode, we will answer some questions.